Hello everyone, Victor is here, your organic chemistry tutor, and today we are going to be synthesizing this molecule on the left from acetylene and any other reagents that we might need. So the first thing that jumps at me right away is the fact that we have a cis double bond over here and we have a trans double bond over here, which means that if we were planning to make our molecule from the corresponding alkyne right away, from something like this for example, then we would have a problem, because there is no way I can, let's say, take one triple bond and convert that into a double bond and keep the other triple bond intact without converting that into a double bond as well. So this molecule cannot be my predecessor, which means that I need to come up with a different way of accomplishing this synthesis. Well, what if instead we're going to be converting a triple bond into a double bond while we already have a double bond in our molecule? What if I had an alkyne like this? Well, if I have a starting material like this, then it's going to be a rather easy job to convert that into my corresponding alkene by using the Lindlar's catalyst and the hydrogenation on the Lindlar's catalyst, where the triple bond is going to be reduced and the double bond is going to be safe. But then we are going to have another problem. How are we going to put this molecule together, bearing in mind that we have to start from the acetylene? Well, probably a good breaking point here is going to be this bond. We can easily make a bond between the triple bond and something else by using the corresponding alkynide anion, something of that sort. Well, in this case, our acetylenide ion is just going to come in and push our leaving group, is whatever that X might be, and give us the intermediate that we want. A bit of a challenge that we are going to have is how exactly are we going to put this X onto our alkene, specifically next to a double bond, but if we remember the radical halogenation in the allylic position, that's not going to be too much of an issue, which means that the predecessor for that electrophile is going to be just butene. So now, when we have the general idea for our retrosynthetic analysis, let's put it all together and see how we can accomplish this synthesis. So I'm going to separately make my intermediate A over here, and also I'm going to separately make my intermediate B before I'm going to combine them together in the synthetic scheme, so that is going to be an example of a convergent synthesis. So for A, we are going to start, of course, with acetylene, which is going to be our starting material for our synthesis overall. Then we are going to treat our acetylene with a strong base, something like sodium amide, in order to deprotonate it, so we can do the alkyl substitution and put the methyl group on that. This acid-base reaction is going to give us our acetylenide anion, which we are then going to react with an electrophile, something like CH3I, where in the course of a simple SN2 reaction we are going to push the iodine away and put the methyl group on our acetylene, giving us propyne. Now, from this point, we are going to treat that propyne with a strong base again, so I am again going to treat that with sodium amide, NaNH2, to deprotonate the left side of my molecule, making an intermediate A. Now, when it comes to the synthesis of my intermediate B, I'm going to start in a very similar fashion. We're going to take the acetylene, we're going to deprotonate it, making the corresponding acetylenide ion, just like in the case above. Then I'm going to treat it with methyl iodide, giving me propyne, again just like in the case above, but then I'm going to do it one more time to add the second methyl group to my molecule and get this butane. Now, from this point we need to convert our alkyne into a corresponding alkene, keeping in mind that that has to be a trans alkene, so we are going to use sodium in liquid ammonia, and make sure that whenever you are using your sodium in liquid ammonia, which is Na in NH3, you do not confuse it with our sodium amide, NaNH2 and Na in liquid ammonia. Those are very different things and they do very different reactions. But I digress. So sodium in liquid ammonia going to give me my trans alkene, and then from this point I need to put a leaving group onto the edge of this molecule, which we can accomplish with radical substitution, so I'm going to use something like NBS in the presence of the typical radical initiator as a B-cis-butyrylnitrile, and that is going to give me the corresponding bromide. Now we can take our intermediate A, which I had right up over here, and I can take my intermediate B over there, and I can combine them together in order to get our ene, so the molecule with a double and a triple bond, that is our main intermediate, that is our predecessor before the very last step. So combining those two things together, we are going to have our SN2 reaction just like we would expect in this case, making our ene, and I'm also color coding all of my parts of the molecule, and I'm signifying this new bond that I have over here with this bright orange line. And the final step here in this synthesis is going to be the reduction of a triple bond. So we are going to use hydrogen with Lindlar's palladium, palladium that has been poisoned by barium, calcium, and lead, typically, in the presence of quinoline, and that's going to give us our target molecule. Easy peasy. Now, the take-home message here is that whenever you are doing any kind of chemistry, in many cases, reactions are not going to be selective, and if you have a certain reaction that can react with a functional group in your molecule, if you have multiple of that functional group, often, if not almost always, that reaction is going to touch all of those functional groups. So remember, molecules don't want anything. They don't know what you want either, and because of that, you cannot just have this wishful thinking and hope that one functional group is going to react and the other equivalent of the same functional group is just going to stay there and do nothing. Whenever you are planning your synthesis, remember that if something can react in your molecule and there is nothing that stops that, well, then just because you don't want that to happen, it doesn't mean that it's not going to happen. Like in this case, it would have been super easy to create the molecule with two triple bonds, but there is absolutely no way I can reduce one triple bond and not touch the other triple bond, which means that I had to design a completely different way how to go about that. And that's all I have for you guys for today. Thank you for watching. Leave me your questions and feedback in the comments below. If you learned something new today, hit that like button to help promote this video and help more students see it. Subscribe to the channel for daily organic chemistry updates. Watch this video next, and I will see you tomorrow.